And I can take it in a micromechanical model and say, okay, now I have a bunch of isolated stacking faults. I know how much that energy costs. I can do a volume average, and I can predict the cohesive energy as a function of carbon concentration and my random faults. And I come up with this equation here. And with some algebra, you can show that these two equations are identical. In other words, anything that sits along here within a sort of non-interacting, if you exclude these sort of local interactions here as energy penalties, isolated stacking faults are equally favorable as the zeta phase. Right? And I think that's a very powerful message. Right? That was actually the second thing I said, and the conclusions that I sort of started with. The first thing I said was that there's no interfacial energy. So we can actually now take our model and compute the interfacial energies using the stacking sequence. And between TAC and the zeta phase, we get identically zero in the model. TA2C and the zeta phase, we get identically zero. And between TAC and TA2C, we actually get this is actually a negative number because locally it's actually formed a piece of zeta phase, which is more energetically favorable than either of these two. So that hits up all of the points that I wanted to make, which is that the top and bottom energy is zero, right? Which will force plate-like growth. Not only that, but an isolated fault really isn't any better, is not really any worse off than a bulk zeta phase energetic. And so that gives us a lot of insight into why this microstructure appears. And we'd like to go back and back that up with phase field modeling if we can, but I don't think it's really going to change my answer. I was asked, and I see that I'm going to exceed my time, I apologize, to talk about future directions, right? And so in this work, one of the things that we're working on right now, right, is we dealt with everything at 0K. DFT is limited in that sense, right? And there's been a lot of questions about how the temperature and pressure affect the stability of the zeta phase. We're working on that right now. We get at that by computing elastic constants to correct that can give us pressure dependence. It can also give us corrections to the free energy, right? And we can also compute entropic contributions in terms of the configurational entropy, so that we can correct free energies to finite temperature. Like I said, we also want to understand the role chemistry plays in stabilizing the zeta phase. So looking at hafnium, carbon, nitrogen, work on this project that we will be doing. And my collaborator and I have already started talking about what we're going to do next. Not even a year into this project, and of course we're planning out. I said before, oxidation is very important. In fact, all the melting temperatures were in inert atmospheres, right? The real problem with these things is, yes, they have very high temperatures, but they're going to oxidize. So the question is, what are those oxides and what are their melting temperatures? How do we get that information in? And that's one of the areas we think we're going to go next in terms of chasing down funding from our program manager. Right? All right. That was part one of my outline. I've already sort of touched on current and future research. I want to go through this, I guess, somewhat quickly on what else we're doing in my lab. We have funding from the American Chemical Society Petroleum Research Fund to actually do fundamental studies on the interfaces of iron carbides. So the motivation of this is steel, right? Steel microstructure is pearlite, and while well studied experimentally, they still don't know what the orientation relationships between the pearlite qualities are. And they have postulated a number of orientation relationships. And so what we're doing is now taking classical atomistic simulations and going there and actually modeling them. So we can identify at the atomic level what is their structure, what are the energetics of the different interfaces, and compare them. So, and that's actually what Matt's working on right now. Other areas that we're interested in, and I can keep going on. I said there are a bunch of stuff I left off that we've talked about today. I've actually struck up a collaboration with Sucker Lee at the University of Connecticut, another experimentalist, and he's got his hands on some very interesting intermetallics. So this is a superconducting material. It is and I'm going to butcher this. It's an iron pimictide. I don't know how to say it. It's CaFe2AS2. And what this thing, the great thing about it is it goes through a number of phase transformations. From at room temperature, it's antiferromagnetic, but if you compress it along the C-axis, it will transform to non-magnetic. And as you can see in Suckwoo's experimentally determined stress strain curves, you get a reversible pseudoelastic effect with very little dissipation and probably 15% strain. We can actually model this with a combination of DFT, so I can strain fundamentally the unit cell. I can wrap this up into micromechanical theory and thermodynamics because it's going to split into phases as I deform. Some of it's going to be high temperature phase, well, antiferromagnetic, and the other half is going to be non-magnetic, half, whatever. The point is we can couple thermodynamics, microstructural modeling, and the input of the DFT to produce a stress strain curve that, for as simple as the model is, it's very simple. We at least get transformation stresses and strains that are very close. And this is work that's been going on for just a few months. So we are actually writing a proposal right now to submit. So he's supposed to send me his draft any day now. The student I co-advise, in fact, is working on modeling deformation twinning in magnesium. I guess most of us know that magnesium now there's a lot of research going on in magnesium. There's a lot of interest in companies, especially the automotive industry, in understanding this material because they want to use it as a lightweight structural material. So we're looking at fundamental studies on nucleation of deformation twinning and how that interacts with dislocations. And that's supported by NSF CMMI. I was asked to talk about proposals. How many proposals? I've read what my proposal writing experience was. Fine. I had to write a proposal to get the Truman Fellowship. And at Sandia, I wrote 4 LDRD proposals. LDRD is like NSF at the National Labs. It's got about a 5% award rate. The advantage is that they decline like 80% of them in the first round so that you don't waste too much time on them. Most of those were declined, but I was awarded the early career LDRD. And okay, this is different, obviously, than external funding. It is internal, but trust me, it's about as brutal as the external funding review, just on a different level. At Drexel, I have 3 funded proposals: FOSR YIP, PR Petroleum Research Fund, Doctoral Investigator Award, and I'm a co-PI on the NSF CMMI grant. I was actually going through these numbers, and it's like, wow, that's all I've written. 7 declined proposals, 6 from NSF, 1 from DOE, and 2 pending proposals in NSF. So there you go, requested information. This was actually easy to pick out of my midterm review package. Finally, I guess I was asked to talk about my teaching interests and activities. At least that's the way I interpreted it. So, and going back to this theme of mechanics and materials, the areas I would like to teach in, feel comfortable teaching in, are in the areas of mechanics and materials. Right? So they asked to identify some undergraduate courses I would teach, right? And you can see that in the mechanics section, it's focusing on dynamics, vibrations, fundamental mechanics courses. Many of the courses that I have experience with are actually taught in your civil department. I'll go over what I've taught here in a minute, but strength of material statics, those courses. So the number of mechanics courses is a little bit reduced. On the material side, obviously, introduction to engineering materials, metals and alloys were the ones I could find. I felt that it was unbalanced, so I just threw thermodynamics in here on the material side. Just felt like I think thermodynamics is a great subject, and we should all teach it. And I like to emphasize constantly that everybody says where I'm at, you're a structures and materials person. You don't do thermodynamics. No, about half of what I do is thermodynamics. Right? Thermodynamics are inherently linked to structures. The graduate level, and I'll start with mechanics, it's a little bit more fun, right? one of the areas, and we talked about this already today, but I think that I can really contribute to is one is teaching a classic course in continuum mechanics. From my perspective, what I think of continuum mechanics, when I see that name, is large deformation continuum mechanics, right? So, the deformation gradient, right? Our students should fundamentally understand this material at a mechanics level. And this is applicable to what I do. And hard materials, it's obviously important for soft materials. Basically anything, and perhaps more important for soft materials, because you're going to more likely see large deformation. A course that I've been interested in teaching for a long time, I actually helped develop a set of notes. You can find them online on micromechanics, right? Which is this course that I would actually change from what we taught at Stanford, the notes I helped my advisor develop, away from what we had there to focus a little bit more applied in basically predicting the properties of heterogeneous materials. And for my students, what I want them to understand is how to predict basic elastic constants of a polycrystal from the anisotropic cubic elastic constants, to make that connection. And that's just not for metals, it's for ceramic, it's for everything. How do I introduce a mechanics framework to translate anisotropic material properties and heterogeneous materials to what we see macroscopically? Other courses I can contribute to, and this is really dependent on time, interest, and working this out with the faculty here. I teach plasticity, right, and which is a constitutive type course. Obviously, another course of interest would be fracture. We had an old fracture mechanics course I found somewhere online. So, again, these are things students should see. You also teach a sort of applied fundamental element course. A lot of experience in fundamental element analysis. Did it for 3.5 years at Lucky, so I can take an approach from the applied side. Also, if there's interest, I can go on the theoretical side, right? So coming from the theoretical group, theoretical and applied mechanics group at Stanford, I took more, the view of finite element was actually a mathematical method to approximate a PDE. And so there are two distinct visions of finite elements that you can take. I've experienced with both. So, and it really depends on the constituency. We go to materials. I know you may have some courses like this, but the descriptions perhaps were a little bit confused. But some of the things I would like to see in a materials type program is thermodynamics of solids, right? Kinetics, and I don't know what you want to call it, structure and symmetry, or but these seem to be some very basic courses that I can contribute to as a faculty on the materials side. And then of course, my dream is develop some computational materials courses. And I don't know, I have to think about this a little bit more in terms of the semester system, because I've always been on the quarter system, so I'm always thinking in 10-week chunks. And so maybe it doesn't make sense to have 2 classes, I'm not sure. But it was easy to break them up is one on the atomic level, right? So electronic structure theory, as well as classical atomistics, and then to go the microstructure level, right? And give students at least an introduction to how do we simulate materials. I'm almost done and only slightly over, which is amazing. Courses I've taught at Drexel, I've taught freshman design, statics, which teach at the civil department. This year, I am embarking in teaching our year-long graduate mathematics sequence. So, math person as well. Students love that. And I've taught an upper division graduate course, Introduction to Plasticity. So as you can see, a lot of this is focused around mechanics and mathematics. Since at Drexel we have our own material science program. And then finally, I've taught strength materials at Stanford. So, I've talked for a while. Probably lost a few of you. But at this point, it's a lot of information I know. I'm more than happy to answer your questions. Thank you for enduring my, I don't know, talk.
Yeah. If it's hard to find, I don't want to ask you to flip back, but when you were dealing with the modeling questions in your research and the permutations that you used to actually right here.
Yeah.
A little, one more forwards, actually.
This way?
Yeah, there we go. Yeah, we were dealing with explaining why those end up being like energetically degenerate phases, and also right around here you came back to the point that these were still in like a largely metallic bonding state. Your DFT calculations give you any indication of like for your stacking fault ordered phases if that changes the extent of metallic bonding locally? And yeah, because I mean, like in order to get this approximation, you mentioned that you had to include an approximation for further order bonding.
Mm-hmm. So does DFT, of course, basically gives you a density, right, of where the electrons are. It's a density cloud, right? So it's basically a probability density of where the electrons are, and so you can plot contour clouds. In fact,
I guess I was more asking just to see if you guys had a speculation on whether or not that like fraction of metallic bonding had changed for that phase.
So in all of these, they have a fair amount of metallic, right? And what actually I was going to go back, but you can actually see this. We did a different study on this, and you can see that based on where you put the atoms, you can actually see the electron clouds and the actual bonds change. And in materials, so we actually compared tandem carbide and hafnium carbide. And because of the difference in electrons, you actually can see the extent of the metallic bonding and the change in the metallic. So, and you have to interpret it. It's interpreted, because all this is, all you're looking at are electron clouds, right? So you can't say it is metallic bonding. We say metallic like bonding simply because we know the properties of the material. And one thing you can look at is, right, if you, one thing is the density of states, the electronic density of states, which are continuous to the Fermi level. And you could go through and do detailed look at how the density of states at the Fermi level changes, which gives you some indication of how metallic bonding, or how the bonding there changes. I'm a little skeptical about extracting too much information from that, right? So actually, that's why I like doing the analytical models that tell us, right, when we do this, we can actually see what I need to include to get that model to work. Because there's really, in terms of DFT, what it actually gives you is the probability where the electrons are, the density.
To switch a little bit, your potential for teaching is quite broad, many areas.
Yeah.
If you had to pick a specific area and one specific course, which one would be your favorite?
It's a good question.
Well, you can't narrow it to two.
No. It's really a full, a philosophy. Do I want to be selfish? Do I want to be what I think is good for the students? Right?
Be selfish. Answer it in selfish.
Selfishly, then I want to develop material modeling courses because my students will take those and will love it. Right? But from my perspective, the way that I deal with my students is I try to get them to take as many classes as possible. I want my students, like I did, try to get, we do so many different things. You said, I do so many different things that I have to have my students exposed to so many different ideas. So I have my students right now go through and take all the mechanics courses. And then I send them to the materials department and have them take a bunch of materials courses. And then as I was talking to Troy, it doesn't stop there. My group meetings as a theorist, I have 4 grad students. I know what they're doing pretty much every day. They're sitting in front of computers. So our group meetings is we go over more topics, right? And we explore what they don't understand. In fact, I had the greatest revelation the other day when one of my students wrote down the equations for density functional theory, and I said, and that's why it's called density functional theory. And they said, wait, why? And I said, because the energy is written as a functional of the density function. And they said, I don't know what you're talking about. I said, oh, we need to learn calculus of variations. Right? So it's always a learning process in my group. We're always trying to learn things. And that's why I love to go over topics like melting temperature of diamond, or sublimation temperature of diamond. Right? I've got to have them learn as much as possible, because I don't know, once they're out of my group, there will be modelers that we're going to expect them to be able to model things. Sorry for that long-winded explanation, but I warned you. Yeah.
You mentioned the elastic constants, developing the elastic constants for the various carbide phases as
Yeah.
one of, as a future research direction.
We actually have done that. We have the elastic constants. We're going more using them to correct free energies. But
Have you validated those experimentally yet?
as much as you can.
Because it's really hard to do platelet phases and things like that, especially when you're dealing with interfaces
Right.
on
So we
nanoscales.
can take in any of these in their bulk character to determine the elastic constants.
Right.
The problem is, if you go to the literature, and we actually, I had a lot of fun. Greg and I wrote a book chapter and just plotted all, or listed all the elastic constants determined experimentally for just rock salt tack. And it's like, trust me, I'm validated by those.
That's
they
the
vary by.
concern. So they're not really constraints for you anymore. Experimental details are not functioning as a model constraint in that case.
They again, are experimental details constraints, of course, right? What I like to do, the way I like to think about modeling is say, how do you know what you're doing is right? It's not. It's a model, right? And so the question I always ask is, did what I do, was it useful? Did it provide insight? If it did, great. In fact, to go back to the elastic constant question, I don't have this plotted, but one of the questions that we had was in terms of fracture toughness. Didn't have time to go into the many things that we've done. Was we said, well, we know that as you reduce elastic constants, materials tend to become more ductile. You get more metallic-like bonding, and you tend to get more plasticity, and so your apparent fracture toughness is going to go up. So one of the things you can do is take DFT, measure the elastic constants, simulate the elastic constants, and look at the trend. And the trend is almost exactly what you expect. No matter what exact phase I look at, as I deplete carbon, I'm breaking covalent bonds, I'm increasing the amount of metallic, and the elastic constant decrease. And you can look at the elastic constants from TAC to T2C, and the 4-3 sits right in between. There's no surprises. So I say, makes sense. You can't measure them experimentally, so that's the best we got. Yeah.
So I was intrigued by a comment you made early on about the zeta phase and that some people have measured a rising R curve for it.
Mm-hmm. All I've seen is the abstract. We just discovered the paper like 3 days ago.
Okay.
And I know who the group is. They're the other group doing similar work. Yeah. So, because we were also have done experimental work and looking at the fracture toughness via sort of the mechanics via indentation. I'm looking at what happens when you take a new indenter and come in at different angles relative to the last. And you can see a very interesting phenomenon in that you get cracking parallel to the last, but perpendicular to them, you get a very serrated feature. But I wish I could answer more about the rising R curve. I've got to read that paper. Yeah.
How does this extend then to developing viscoelastic tensors and the coefficients that go along with it to predict damping in materials structures, especially with anisotropy?
So, okay. So if we want to predict like, viscoelasticity, you mean, or viscoplasticity?
You'd probably think of it as viscoplasticity. We kick in the other coefficients beyond just the elastic coefficients.
Okay. So, let me, there are two ways to go, right? One is I could say, if we look at just the quadratic behavior, Is that what you're talking about, going beyond quadratic behavior to
Going to a
anharmonic
point where we can
elastic?
start to predict losses in materials versus elasticity.
Mechanical losses. Well, there you have to have some sort of typically defect motion, right? So you're either talking about dislocation motion, point defect motion, and
In crystal structure.
in crystal structures. Yep. So that's something my advisor has worked on for a very long time, and that will take many, many PhD dissertations to get there, starting from here. It's an interesting route. We actually have some. It's probably better to start on the experimental route. And what actually, one of the things that Greg is doing is actually looking at developing methods to test them at high temperatures, because this is a real problem. And I'm sure Troy's familiar with this, but they've actually developed a non-contact tester with they're using Joule heating and Lorentz forces to mechanically load them and start to measure them. So one of the things you start off with is what are the high temperature responses of these things. That's an area we're targeting, and that's a very tough thing to do.
So that Don asked one question.
Yeah.
That's important in our department. The other question that's important in our department is electronic behavior materials.
Mm-hmm.
And selenium, I think, maybe Jason will correct me if I'm wrong, but gallium that with cat-tal, you can lower the band gap. Is some of the theory that you utilize and so forth, can you back out the band gap, and can you
So
determine the like vacancy, and how it behaves in p-type and all that sort of stuff?
you can get to that. So right, as I said before, you can compute density states. Now, if you start to talk about band gap, you have to be a lot more careful, because the methods that you use in DFT are good. And one of the reasons why we use them is they're very transferable. They work in a lot of cases. So, and you can simulate band gap. You have to be very careful. So the uncertainty there, in particular for predicting band gap in semiconductors, is not great. And so that requires a lot more investment in developing and testing the exchange correlations that they use. And those that they use, so we use some fairly standard ones because they work very well in predicting bulk material properties. You have to play some games to get better estimates of band gaps. So you could do that. And ours have the band gap, right? They're essential conductors. So you can simulate that, but again, there are some pitfalls there. I would say certainly DFT can do it, but beware.
So I had a kind of related question.
Yeah.
We're all wondering about whether we can collaborate with you. That's why we're asking you these questions. Does everything you work on wholly crystalline materials? Do you do amorphous or semi-crystalline material modeling?
I haven't. Doesn't mean I can't. I mean, amorphous materials is part of, the broad name of material science.
Right.
I've gone to the talks. I don't do it because I haven't gotten funding.
Right.
But certainly these methods, whether, and I would go more towards classical atomistics if we're talking,
Right.
bulk metallic glasses or things like that, but they're certainly amenable to doing those simulations.
Right. And then when you talk about your DFT calculations, as someone who's never done this, help me understand, do you write your own code and algorithms to do this? Are you using commercial products to do this? How do you
We use VASP. So it's basically the first one that came out. You pay a one-time, it's from the University of Vienna, and that's the one we use. I inherited that use from everyone else. Most people use it simply because it's trusted. But we write a lot of stuff around it. Right? It is limited in its capability. Like, for example, to do stress strain curves of these materials, they're not made to do. It's not made to do stress strain curves. We got to write our own wrappers and all that stuff. The one good thing that two of the tools that I use, density functional theory and classical atomistics, have done is you know, there are a couple fairly standard codes out there. So fast, and I think the other one that it's actually freely available is quantum espresso. A lot of people use. I don't use it simply because I use it. Right, I have all my stuff developed for this one code. We just run that. On the classical side, the biggest one out there for hard matter is lamps. I understand soft matter people grow max for NAMD. So I don't use those because I'm not a soft matter person. So lamps actually comes out of Sandia, or it was. I've worked extensively with those people. I know the developers. I've written stuff into lamps. It's a great program. Yeah, but other stuff we will write ourselves. It varies. You know, point out, I started off as a PhD student doing a method called dislocation dynamics, which is a defect evolution code. And I spent half my PhD writing code. So it's not that I don't know how to do this or haven't done it. But again, it depends. It's like you go out there, you look what's available, you take what you can use, you write what you can. Yeah.
So I saw you had one DOE proposal. So who did you collaborate with, and what part of DOE was that for?
Okay, great question. One DOE proposal, yes. That was who did I collaborate with? I'm pretty much sure it was everyone. This was the, we put in a proposal for one of their big centers.
Okay.
So it was a number of people, it was, I don't know, 15 people.
Okay.
Right, Mitra Taheri was the PI.
Okay.
All right, and I forget exactly what center call that was, but it was one where they actually they didn't even have enough money to renew the ones that were up for renewal. Yeah. It was a.
And what was your role in that? Because
right.
High temperature.
So we were actually, yeah, it was my role actually in two areas. So me and a colleague of mine were looking at doing atomistics. They were interested in basically microstructure tuning for radiation damage and mechanical extremes. So my role, I was selling myself more as a mesoscale person, saying that I can develop the constitutive laws, do the microscale finite element, and and connect back to the people doing atomistics. There's another guy at Drexel who does atomistics for hard matter, and he was taking on that role. So we were on sort of the simulation side to try to help them organize and tune their microstructure for radiation and mechanical extremes.
We should probably call them into this.